Thanks a lot for coming and watching this tape. I'm going to talk about input-output. Now, input-output is an area that's been an orphan of computer architecture, long neglected. So I'm going to need to motivate why you want to stay and watch this tape. To give you an idea how much this area has been neglected, first of all, the whole equipment is referred to as peripherals as opposed to the central processor. And secondly, there was a programming language that was the ancestor of most of the programming languages people use today. This programming language called L=60, and when it was invented, it didn't have any input or output at all in the language, and nobody cared. So let me motivate why you want to watch this tape. Starting off with our first slide. What's happening is a renaissance in CPU performance, improving by 50% to 100% per year. In fact, what we have today is the supercomputer in the desktop. It's something that people have been talking about for a long time. What you see on the left-hand part of this slide is the HP 735 workstation and the various characteristics of that. In contrast, on the right-hand side is the Cray 1 supercomputer, the original vector supercomputer and its characteristics. When you line these characteristics up, by all measures, the HP 735 is faster or better than the Cray vector supercomputer, even including the cost at about 1% or 0.5%. Another way of saying that is that the HP 735, if it was announced in the late 1970s, would have been a hell of a good supercomputer. So we've got the supercomputer on the desk. What an amazing development. Moreover, people are taking tens or hundreds of these processors and putting them together to create supercomputers out of lots of these processors. So that is moving at an even faster rate, say 150% per year. So why do we care about I/O? Well, because I/O hasn't been moving as fast as the processor design. It's limited by mechanical delays and has been growing maybe 5 or 10% per year over that same time period. What's going to happen if we don't improve the I/O component? Gene Amdahl came up with Amdahl's law that says system speed is limited by the slowest part. So let's do a specific example. If we spend 10% of our time today on I/O and we get a 10 times faster CPU, which comes along pretty quickly, we're only going to get half of that performance potential. We're going to lose 50% of that performance. Similarly, if we take that same program with 10% of its time today and get a 100 times faster CPU, possibly with a multiple processor, we're going to lose 90% of that, getting only 1/10 of its potential. That means we have an I/O bottleneck facing us very shortly, because a diminishing fraction of the time is going to be spent in the CPU in the future if we don't do anything about I/O. That means a diminishing value of faster CPUs, which means a diminishing value of researchers who are working on CPUs, not to mention a diminishing value of high-paid academic consultants on CPUs. So I think we all agree this is pretty important, even if we're not going to work on I/O ourselves. So what have our colleagues in magnetic disk design been doing all these years while we've been making processors faster? They've been concentrating on capacity and dollars per megabyte. They are improving at about 25% per year historically, and more recently at about 50% per year, both of those measures. The other thing that they've been doing is evolving to smaller disks, from things that were the size of washing machines or refrigerators to things that you can fit in your hand. Here's a specific example. So the disk I have in my hand is a 2.5-inch diameter disk. You can see it's very thin, maybe a 1/2-inch diameter, and what's on the back of it is the electronics, all the integrated circuits. This disk, in the time we're making this tape, can hold 320 megabytes. As you can see, there's just 2 platters here. This is remarkable shrinkage in design. That's what our disk colleagues have been doing, making things smaller, the cost cheaper, and the capacity greater. That's what they've been doing. And in fact, in a few years, this is going to seem like a dinosaur monster disk, and people are working on disks that'll be 1 inch in diameter, much smaller than 2 inches. You won't even be able to know whether I've got one in my hand or not. What our colleagues in the disk industry have been doing is making disks that are smaller and cheaper as opposed to larger and faster. The faster processors need larger and faster disks. So the question we asked ourselves 6 or 7 years ago was, can these smaller disks be used somehow to close the gap in performance between disks and CPUs? Or how could we use these smaller disks to do that? So the idea is to replace a small number of large disks with a large number of small disks. This next slide shows how it would work. What we'd see on the top is the way disks are traditionally manufactured. What you see is 4 different designs having 4 different engineering teams, each concentrating on the high end to low end of the efforts. What we're talking about instead is concentrating the engineering talents in the lowest, smallest diameter disk, build the best disk you can, and simply replicating to get mid-range and then high-end designs. That's the El Dorado of disk array design here. That's what people are trying to do. Well, how well would that work? What's shown on the left column is the IBM mainframe disk. Back when IBM made a lot of money, this is where a lot of money was made, in the mainframe disk. If we contrast that with a narrower disk, also from IBM, which is in the middle column, we can see some big differences there. But if we got enough of those small disks, in this case 70, so that we would get the same capacity, that's this right column, see, same capacity, we have some interesting characteristics. First of all, it's actually got some advantages in size and power, but the really exciting advantage from the system designer's perspective, given this CPU performance gap, is the data rate or I/O rate. Data rate, megabytes per second transferred, or the number of I/Os per second. Given that we have 70 disks with 70 arms operating at the same time instead of just a small number, we can get a much higher data rate. You can see that's about a factor of 8 improvement. Even though the big disks run much faster, we've got so many small ones that are close enough, we get a factor of 8 improvement. And the number of I/Os per second similarly increased by about a factor of 6. And let's say the cost is about the same. But what about this last row here? What about the reliability? This is an acronym for the mean time to data loss. So you can think of it as the mean time between failures. How well will that work? Well, it turns out if things fail randomly, then the reliability of n things is 1 over n. So we take the mean time between failure from about 50,000 hours divided by 700 hours. In other words, the mean time between failure drops from 6 years to 1 month. Therefore, disk arrays are too unreliable to be useful. Therefore, it's a bad idea. And this is the end of the tape. Thank you very much. No! Don't hold that dial. What we're going to do is add extra disks and turns a weakness into a strength. Hence the name of RAID. What we're going to do is take redundant arrays of inexpensive disks by having some extras to overcome this reliability disadvantage. Now there's 2 advantages here. One is subtle and one's obvious. What we're going to do is have extra disks so that when a disk fails, we can reconstruct the lost data. That's the first point. But if we can reconstruct the data sometimes, that means that on the fly we can reconstruct the data that's been lost. So just because at the end of the term when everything's busy, a disk crashes doesn't mean you can't get your term paper, because it can be reconstructed. It's going to run a little slower, but reconstructed on the fly and given back to you. We'll see a tape of that later, a demo showing it runs a little slower, but the information's available continuously. And that's the basic idea of RAID, of this redundancy. That's one application of the technology, is to help the global change researchers. But another interesting application is the electronic library or digital library, and you can see that on the next slide.